Welcome to this explainer. Okay, look down at the shirt you're wearing right now. Have you ever actually stopped to wonder exactly how it was made? Well, today, we are going to turn the clothes on your back from a total mystery into a masterclass on textile engineering. We're going to map out the entire classification of yarns using a simple, absolutely unforgettable visual framework.
Today, we're taking a taxonomic tree approach to break all this down. We'll be looking at the basics of yarn, the staple spun family, spinning staple yarns, yarn construction basics, the continuous filament family, and finally, specialty and covered yarns.
All right, kicking things off with Section 1, the basics of yarn. Before we can even get into the complex stuff, we kind of have to start with the trunk of our tree, the raw materials.
The fundamental distinction here is actually beautifully simple, and you'll see it laid out in these bullets. A textile fiber is your basic building block, like natural cotton. Assemble those individual fibers into a continuous length and bam, you've got a yarn. For your memory hook, just think of staple fibers as tiny Lego blocks snapped together in a long line, whereas continuous filaments, they're like endless unbroken strands of spaghetti pulled straight from a machine.
And that brings us to this brilliant visual right here, the comprehensive yarn classification tree. Notice how it immediately splits into two main boughs? You've got your staple spun yarn on the left and your continuous filament yarn on the right. Literally everything we talk about today is going to trace back to this exact diagram. So let's move right into Section 2, the staple spun family. We're going to climb up that left side of our tree first and explore those Lego-like building block yarns.
The absolute most fundamental division here is length. It's a super easy split to memorize. The magic number is 60 millimeters. Anything under 60 millimeters is a short staple yarn. Think everyday cotton. Anything over 60 millimeters is a long staple yarn, like wool.
Now, zooming in on those short staple yarns, we've got two primary processing methods, carded and combed. During spinning, carded yarns don't actually have all their short, messy fibers removed, which leaves them a bit less compact. But combed yarns use an extra machine, literally a combing machine, to pull those short fibers right out. So your memory hook here? Just remember that combed means cleaner and compact. Taking that extra step yields superior strength, a much smoother texture, and a really nice lustrous finish.
When we look at long staple yarns, we get this really fascinating contrast across three main types, which you'll see in the bullets here. First, woolen yarns. These completely skip the combing step to stay bulky, hairy, and soft, which is exactly what you want for a cozy sweater. Second, worsted yarns. These are fully combed and parallelized, so they're smooth, crispy, and incredibly durable, the absolute ideal material for a sharp, lightweight suit. And third, sitting squarely in the middle, is semi-worsted, which skips the extreme combing, making it totally perfect for something like a blanket. All right, shifting gears to Section 3, spinning staple yarns. We know the types, but how do we actually lock these short fibers together to make the yarns we just talked about?
Let's matrix this out. Engineers have developed some truly incredible machinery to twist these fibers into yarn. You're definitely going to want to remember the king of ring, because ring spun is by far the most common, giving a strong, soft, and compact yarn that's great for almost anything. But, the industry needs speed and variety too. So we have rotor spun, which uses a spinning rotor to sacrifice just a bit of strength for a less hairy yarn, perfect for heavy denim or terry towels. And then there's air jet spun, which trades physical twists for sheer air pressure, creating a twistless core that is ridiculously abrasion-resistant, perfect for rugged workwear and sheets. Now, before we list the next set of highly specialized spinning systems, I want you to lock this exact phrase into your mind. Friction equals vacuum and perforated drums. Seriously, if you just picture a vacuum pulling fibers onto a rotating drum, you'll easily recall exactly how friction spinning works.
Because honestly, engineers have invented incredibly clever ways to combine fibers for highly specific strengths, as shown in these bullets. Friction spun yarn, using those vacuum drums, gives a wonderfully soft handle. Core spun literally hides a core material like polyester inside an outer wrapping of cotton. Wrap spun uses a continuous filament to hold a staple bundle together using a hollow spindle. And my absolute favorite, self-twist, it cleverly gives two components alternating twists in short segments, so when they touch, they naturally self-twist together. Brilliant, isn't it?
Moving on to Section 4, yarn construction basics. Let's look at how this builds, literally.
This sequential build perfectly demonstrates how we get from a super fragile single strand to heavy-duty industrial ropes. It's a simple four-step process. You start with a single yarn, twist two or more of those together, and you have a plied yarn. Twist those plied yarns together, and you get a cord yarn. Finally,
Twist cord yarns together and you achieve an incredibly strong cabled yarn. It's just a perfect architectural progression.
Now, while these simple yarns we just looked at are completely uniform, fancy or novelty yarns are all about aesthetics. They typically use three parts: a core base, a decorative effect strand, and a binder strand to hold the whole shebang together. If you've ever felt a bumpy slub yarn, a loopy boucle yarn, or a fuzzy chenille yarn like the ones listed here on screen, you are experiencing the highly textured, aesthetic side of yarn construction.
Okay, leaping all the way over to the other main bough of our initial tree, we enter Section 5, the continuous filament family. Welcome to the world of our continuous spaghetti strands.
Remember how all man-made synthetic fibers, along with natural silk, come in continuous forms? Well, this classification is wonderfully straightforward. It all comes down to exactly how many strands you're working with. If the yarn is literally just one continuous piece of material extruded from a machine, it's a monofilament. But if you group multiple filaments together and twist or intermingle them, it's a multifilament.
Now, a completely straight filament isn't always the most comfortable thing to wear. That is where surface treatment comes in. To remember this, think of flat yarns as airbag material. They're tightly packed, super smooth, and they literally block air from passing through. Textured yarns, on the other hand, have been mechanically altered to have permanent crimps, coils, or loops. This creates physical space in the yarn, giving your clothes high breathability, moisture absorbency, and that really cozy aesthetic of a spun yarn.
And finally, we reach Section 6, Specialty and Covered Yarns. Let's look at the highly specialized, high-tech leaves at the very edges of our family tree. These are the materials that are truly pushing the boundaries of what fabric can actually do. First up in our bullets, we have bicomponent blends, which are engineered at the molecular level with two distinct polymers mixed right at the extrusion stage. We've got tape or split film, literally thin sheets of polymer cut into ribbons. Then there's elastomeric yarns, like spandex, that can instantly recover from a massive 60% extension. And even metallic yarns, made of extended metal strips. From stretchy spandex to those high-tech bicomponents, these are the yarns making our modern activewear actually function.
But here's the catch. An elastomeric core is often way too exposed or sensitive on its own. So what do? We cover it. We can wrap it once for a single covered yarn, wrap it twice in opposite directions for a double covered yarn, or, get this, we can literally blast it with an air jet to entangle protective filaments right into the elastic core for an air-covered yarn. And that brings us to the absolute edge of our classification tree, which leaves us with a pretty fascinating question. Considering how far we've actually come from basic hand-spinning, short cotton staples, all the way to molecularly engineering bicomponent spandex wrapped in air-jet protective filaments, what incredible new revolutionary materials are waiting to be spun next? Thank you so much for exploring the yarn family tree with me today. Keep asking questions, and I'll catch you in the next explainer.